Now, let me go back to our block diagram, by now very familiar block diagram of the electronic systems. We have covered most part of this block diagram. There is one very significant important part that needs to be covered, and that is this part, the controller. We are able to sense signal, analog signal from the plant, pass it through analog signal processing, pass it into the A to D, and in the discrete domain, the moving average or glitch filters can be built. And after that, you have the feedback signal. And this feedback signal is compared with a reference or a set point. And on comparison, you get the error, and the error is passed through a controller, and the output of the controller is processed in such a way. Normally, it modulates a PWM block, and the output of the PWM block is a pulse width modulated signal which goes in as control input to the actuators in the plant. So the actuators in the plant can be motors, can be solenoids, can be relays, and they are operated with the help of semiconductor switches, either single switch or in the form of full bridge circuits, which we have studied, along with the respective gate and base drives, which also we have studied. So this part on the controller in the discrete domain, this controller exists in the discrete domain, the algorithm has to be written in the discrete domain, because today most of the controllers are inside the microcontrollers. And this is what will be the focus of this topic, and this is what we will be discussing. So let us try to understand this part and complete the overall understanding of the electronic systems bird's eye block. So let us now get down to designing digital or discrete controllers for the electronic systems block that we saw. And before we do that, we need to understand some terms which are used in the controls literature, so that we understand them and then map them into what we do, or map them into our electronic systems engineering block. So first question that we need to ask is, what is a plant or a system, or how do you distinguish them? So let me put this block here, and I'll call this one as the plant to be controlled. This is the plant that we need to ultimately control. So any plant in a generic form, it has a framework, can be modeled in such a way that they can they can kind of be compliant with 4 generic ports. This is one port, energy port, which we can call it as a source or a sink. There is another energy port. Again, it can be a source or a sink, depending upon the particular instant of time, whether a particular component is sourcing or sinking. For example, a battery, which can source at some given points in time, and which can also act as sink when it is getting charged. So at any given point in time, the power flow can be in this direction. So in that case, this port will be a source port, which is going to pump and push the power into the plant, and the power going out of the plant into a sink. So this is the sink port. So you could also have the reverse direction, where here the source at some point in time can be acting as a sink, and the load can be acting as a source at certain points in time. For example, if I'm having a battery here and I'm connecting it to a motor or electric vehicle, when I'm motoring, power is flowing from the battery into the motor to drive it. When I'm braking, the inertia in the vehicle operates the actuator as a generator and pumps the power in the reverse direction and charges up the battery. So these things could happen. So that is why I am indicating it as a bidirectional power port or bidirectional energy port. And now, so I am indicating here as a single arrow direction, but keep this in mind that it could be bidirectional. There are two other ports which does not involve power, and one of them is the control input to the plant. The other one is sensing port, which senses the important signals and parameters from the plant to be controlled, and this is fed back to some process. And this process, what this process is, we need to describe, find out. And this process will give a control signal which will act as a control input, which will be given to the plant, and the actuators within the plant will act accordingly in so as to control the flow of power or the parameter. So this is how a plant will function. So this plant to be controlled, right? Whatever will be the parameter that needs to be controlled, the control input, the feedback signal, and the process all together, put together, is the system. Very similar to the electronic systems block diagram which we put up in the beginning. So that is the system. Plant is the plant that needs to be controlled. It is generally the uncontrolled equipment that is called as the plant. Let us try to understand this plant and the control system with some real life example. So let me play this video. So this video is that of a tap. You see the tap is acting as a control input, and there is a flow which gets controlled. Okay, so this is a control system, in fact. So let us try to see if we can map it to the framework that we have discussed right now. So tap water control system. So let's see if we can map it to the framework that we have. So this is the plant to be controlled. So there are 4 ports, I said. So this is one port where there is an inlet of water and there is outlet of water, and then there is some tap that is controlling the flow of the water, right? So this is water flow input. This is one of the ports, so I am indicating it here. And water flow output, this is the other port. And then you are measuring the discharge measurement, the flow measurement. So that is being measured and brought out as the feedback signal. And the feedback signal is passed through a process, and it generates the control signal or the control input, which will control the actuator. In this case, the actuator is this tap knob. So this part here, the measurement of the feedback signal is done right now in this particular example by the eyes of the human. The eyes of the human measures the discharge coming out of the tap, and there is a process that goes on in the brain of the person and generates a control signal which wherein the locomotor, which is the hand here, tries to control the actuator, which is the tap knob, in order to adjust the water flow. So this is the tap water control system. But the key takeaway is whatever control system that you see, observe in real life, try to map it into this kind of a framework, this 4-port plant framework. Then from there it will become very easy for you to design and develop even complex controllers. Next, I will show you another example. This is a very complex example of a control system, and this is a person riding a bike. This is my student who is riding this bicycle, and there are several things in play here. So it's actually a multi-input, multi-output kind of a system. So if you see, he is actually controlling the bicycle handle to control the direction. There is something that he is controlling the pedaling action. And also he tries to balance the bicycle so that it doesn't fall. So all these activities are going on. It's a complex system. Let us see if we are able to map this complex system into the framework, control framework that we have discussed. So first, so let's say this is the plant to be controlled, which is the bicycle, riding of the bicycle. What is the input? So the power input is coming from the person, so which basically means the stored energy within the person, which basically means also that the food that he would have eaten is the cause of the source of the energy coming from it. So what are the outputs? One is the speed at which the bicycle is traveling. The direction. So you see the handle, bicycle handle, which is used to control the direction in which the bicycle moves. And balance. The bicycle is like an inverted pendulum. It will fall off if it is not balanced properly. So balancing is the third important action that is happening. All these are happening simultaneously, and that is why it is a very complex control problem. So first, what is being measured to give feedback? So one is the speed that is being measured, and that is measured by means of the driver's or the person's eyes. So eyes is the measuring instrument. And second, the direction. The measuring instrument is also the eyes, and that is being measured and given. And then the balance. The balance is felt by the person, at the cerebellum. There is a feeling of a balance that comes in, and that input is what is also taken. So all these are inputs taken from the person, passes through a process in the brain of the person. The brain of the person is the microcontroller or the DSP in this case. So that is processing and gives the control signals. The control signals, one of the control signal gives signal to the actuator so that it can control the speed. The actuator for that is the pedal. So from the brain, one of the control signals will pass on the information to the locomotors on the legs of the person, which will actuate the pedal wheels. And the second one is the direction. And again from the brain, you have the nerves going to the hand locomotor organs and actuates the handle. And the third, the balance actuator, the person will swing his body to and fro in order to maintain the balance so that it keeps the whole bicycle and the man bicycle system from falling. So this has 3 control inputs and 3 controlled outputs. So therefore, It is a 3 control input, 3 controlled output system, also called as 3 input, 3 output system, also called as multi-input, multi-output system or MIMO system. So this is actually a complex system. So this man on a bicycle is a very nice control problem, but the important key takeaway is anything that you see which is a control system, or most of the things that you see around you will be a control system. You need to map it into this framework that we have discussed. Then from there on, designing the controller is the next job. Let me take another example. This is an example of an electromagnetic system. So where you have this motor, which is the electromagnetic system, you have the rotor here, and there is a speed control regulator here which needs to be turned in order to regulate the speed. Okay, so it's a single input, single output system, but a class of system known as the electromechanical systems comes also as a mechatronic system. So you see the shaft rotating, and the input here coming, the actuation input coming from here through the hand of the experimenter in this case. So you can move the motor at speed, or you can slow it down, bring it to rest. All those things can be done. So this electromechanical system, let us see, can we put it into the framework that we have discussed. So this is the plant to be controlled, which is the motor shaft, and you have energy coming in from the battery or the grid. It is coming through the wires, and the output is your shaft. So on the rotor, you have the shaft, so the shaft speed or the rotor speed. So you measure the shaft speed. You can measure the shaft speed through the eyes of the experimenter. You can also measure all these parameters using transducers. We will come to that later. But right now, the eyes can be used, and the feedback signal comes, processes through the brain of the experimenter, which will generate the control signal, and the motor action is through the hand, and the hand will actually turn the actuator, which will control the shaft speed. So this is how the control system works, and this is in the framework that we discussed. Of course, there can be a lot of changes that can happen in the sense that the sensing need not be from the human sensing. It can be electronic sensing. There can be encoders, tachometers, which will be sensing, giving the signal, and the signal will be passed through the analog signal processor, goes into a microcontroller, control input, which will actuate another motor, which will turn this, which will actually turn this regulator and control the shaft speed. All this can be multiple different ways can be thought of, but first you will have to get the framework right so that you can design the controller properly. So you could also consider this as a multi-output system where you can also do a position feedback. You can control the shaft position by giving a position feedback, at what angle it has to be positioned, and the control input accordingly can also give a shaft position actuation. So there are many applications: vibrators in the mobiles, toy cars, copters, drones, fans, blowers, pumps, compressors, spindle motors, feed motors, electric vehicles, locomotives, so on and so forth. And I recommend that you keep looking around you. You will see hundreds and hundreds of control systems. All I request of you is mentally visualize this framework and try to put everything into this framework. The plant is a 4-port system, and then the feedback is given to a process, and the process controls the actuators in the plant. So this is something that you need to keep practicing, and then we go further in discussing how to build this process and the controller. Let us now represent a generic control system. It will look very similar to our electronic systems block diagram that we discussed right at the beginning of the course. So this is the plant to be controlled. It has 4 ports, 2 power ports, 2 signal ports. One is the control input, another is the sensed output or the feedback port. And the signal from the sensed output, the feedback signals are passed into a process, then goes into the control input. Now let's see, what is this process? Let me have a comparator here, plus, minus, and the sensed output, the signals, are given to the minus input of the comparator. This is called the feedback signals. This is the reference signal or the set point. It is also called the command signal. It's also the desired value, what you finally want the output or the sensed output signal to take, what value that it needs to finally take. So this is the error. The error is passed through a controller, and the output of the controller becomes the control input, which will finally actuate whatever is the actuator that is there within the uncontrolled plant. So generally now all the systems are divided into 2 parts, where you have the analog world. Most of the uncontrolled plant or the plant to be controlled exists in the analog domain, and most of the control aspects exist in the digital domain. So therefore, to take these sense signals into the digital domain, we need to have an A to D. We saw that through, this is just a line which I am drawing, which means that there is analog signal processing involved. And going back into the analog domain is D to A. PWM is one such mechanism. So this generic control system that we saw is actually mimicking what we actually discussed right in the beginning of the class of first block diagram, which gave a bird's eye view of the entire electronic systems, any electronic systems. So the main topics that one would need to understand in order to build and design a controller would be the plant itself, the modeling. What it means is the plant is there. So what about it? You need to have a mathematical representation. And that mathematical representation of this plant is called a model. So you need to have a model and how to know how to go about doing modeling. Then the state equations. State equations is one of the most important modeling tool, and that is something that will represent a system in its wholesome way, along with initial conditions, whether it is linear, non-linear, all those things. Transfer function is another way of representing the system. However, it is limited. It is for linear time invariant systems, and also it does not represent the initial conditions of the memory storage elements. Then, because you have the digital world and analog world coming in together, you need to know digital analog transitions. You know how to go from the analog domain to the digital domain, back from the digital domain to the analog domain. So therefore, Z transforms, sampling, continuous to digital domain methods, and then comes the controller design. PID controller, we have the classical method of designing using the root locus method, and also the modern method, what it is called, the state space method. Then sensing and estimation, one could use for sensing transducers, or one can use also algorithmic estimators like the Kalman filters. Or the swarm optimization filters, these kind of filters, which are available both sensing using transducers and sensorless estimation. These are the major topics that would be needed in order to design the controllers. We will not be doing any generic modeling in this course. I will probably take a specific example and a specific model. We have discussed something on the Z transforms and sampling. Continuous domain to digital discrete domain transitions we have not yet discussed, but whenever it is needed, I will just introduce it there, but not in an exhaustive way. PID controller we will discuss, and we will discuss using the classical method of root locus. I am not going to discuss the state space method. And sensorless estimate sensing using transducers, we discussed the analog signal processing and then the anti-alias filter and all those things. But I am not right now going to discuss sensorless estimation in this course. So, but the key takeaway is these are topics that you should be knowing to do any advanced controller. But we will try to focus on trying to build a PID controller using classical methods.